Hello again and welcome to John's Electrical and Electronic Principles and Science channel. We're going to continue today with reactances and we're going to continue looking at inductive reactance. Now we can see a circuit here. It's got 230 volts on it, an inductor, and what we'll say is under DC conditions that has a current of 50 amps running through it. So it's 50 amps running through the circuit at DC conditions. So if we know that information, then we can work out the resistance of the coil. This resistor here is just going to be an illustration of the resistance of the coil, if you like. And what we can say is, with Ohm's law, V is equal to I times R. So if we want to know the resistance of it, and the current running through it is going to be 50 amps DC, then we can say that the resistance R is going to equal, by transposing this, is going to equal V over I. So the resistance is going to be 230 divided by the current, which is 50. So that would give me a resistance of 4.6 ohms. So we're looking at DC conditions. Now, if this was running AC, different principles would apply, because this would now have a reactance in there. Your coil would have a reactance, which is XL, which is inductive reactance, and that inductive reactance would push against the supply current in the circuit, and then it would drop the value of the current due to the magnetic field expanding and collapsing around that coil. The magnetic field will form, it will collapse, form and collapse. That will induce an EMF which fights back against the supply, and therefore you get a less current in there. So let's say, for example, that current is going to be 42 amps AC. So what we want to do then is calculate the impedance of this circuit, the inductive reactance of the circuit. So the inductive reactance is just the value of that as you would oppose the current, like a resistor, if you like an AC resistor. We want to calculate the impedance, so that would be the resistance and the inductive reactance taken account of, and we want to calculate the inductance of the coil itself. So if we start off with the impedance, then Z will equal V over I, because now Z is the impedance, and that's acting as though that's the whole of the circuit resistance, if you will. So we can say Z, the impedance, is going to be 230 over the current in AC conditions, which is 42. So that will give me a Z value of 5.47 ohms. Okay, so now we can calculate the inductive reactance by transposing the impedance formula. So we know impedance, Z, is equal to R squared plus XL squared. XL being the impedance, R being the resistance. And so we want a value for XL. So we're going to have to transpose this. So if we transpose this formula, and if you notice, it's just Pythagoras' theorem, because these things are all acting together as though they were triangles. So if we said Z squared is equal to R squared plus XL squared. So we're looking for this part of the equation, so we want to move that over, the R over to the other side. So it's plus R, so we do the opposite when we take it over the other side, the equal side. We can now say that to move this across then, Z squared minus R squared is equal to XL squared. And then to get rid of that square there, we can say XL is equal to the root of Z squared minus R squared. Okay, so what I'm going to do, I'm going to clean this off, and then I'm just going to pop the numbers in. by popping the numbers in, we can say XL is equal to the root of 5.47 squared minus 4.6 squared. So that's the impedance minus the resistance. So we can say XL is equal to the root of, and we just total up these numbers. So it's 29.92, that's 5.47 squared, subtract 21.16, so XL will equal the root of those two added to those two, 21.16 minus 29.29 minus 21.16, and that'll give me 8.76. So that'll give me an XL, or inductive reactance, of 2.95 ohms. So what does that mean? So that means that under AC conditions is behaving like a resistor of 2.95 ohms. Now what we want to do now is find the inductance, the value of inductance of that inductor. So the L value. So we need to find the frequency first of all. So what we're going to say is this circuit has a time period, a T, of 20 milliseconds. So with that in mind, if we remember our old formulas, F frequency is 1 over T, so that's the time. So we can say frequency is equal to 1 over 20, and it's milliseconds, so it's times 10 to the minus 3. So the frequency is equal to 1 over 20 times 10 to the minus 3, that gives me 50, and that's measured in hertz. So next, if we want to find the value of inductance, we can say XL is equal to 2 times pi times R F times L, and so we want the L. So all we have to do, these are all connected together by multiplication signs, so if we divide by these lot, then we leave L on its own. So we can say XL divided by 2 times pi times F will equal L. So if we now drop in the figures, we can say L is equal to the XL value, which is 2.95, divided by 2 times pi times 50. So L is going to equal 2.95 divided by that lot worked out, which is going to be 314.15926 54. So that'll give me an L value of 0.009390 henries, or if we move the decimal point 1, 2, 3, so the inductor equals 9.39 millihenries. Okay, so we've now found the value of the inductor. I'm going to clean the board. Oh, what we can do now is work out the power factor. So the power factor of the circuit is going to be R over Z. So that'll give me a power factor. It's going to equal 4.6 divided by the 5.47, the impedance, which will give me a power factor of 0.84. We can now work out the angle that the current lags the voltage, because with inductors, if we remember civil, then the inductor, at the inductor side, the I is lagging behind the current, leads the current in capacitive circuits, lags the current in inductive circuits. And now we can find the angle that I is lagging behind V, and we can say that angle phi is going to equal cos to the minus 1 of 0.84, and that's going to give me an angle of 32.75 degrees. We'll have a look what that looks like now. So I'm going to clean the board off. So if we say our voltage is always our reference, so the V is there, and I is going to lag V by about 32.75 degrees, and we can say that I is going to be going something like that, and the difference between the peaks is going to be 32.75 degrees. Okay, good. All so far so good. So now, if we wanted to calculate the value of a capacitor that would cancel that effect and bring these two more into phase with each other so we don't lose so much power, then what we could say is we could connect a capacitor in parallel with a coil. If in real life, if it was cancelling out the load, it could be connected at the motor, or it could be connected at the supply incoming point, or in fact we could even run a synchronous motor and change its excitation to give it a leading power factor, which would then cancel this out. But what we're going to do now is we're going to look at the value of capacitor to be used in order to cancel this out. And if you remember, our capacitance formula, XC, is equal to 1 over 2 pi times the frequency times the capacitance. So we want the value of this, and we know this XC is going to be the same as our XL value, so we'll just drop that in. So we're going to swap those, pardon me, so we could say C is equal to 1 over 2 pi F, and the value of XL that we want to cancel out. So we can say C is going to be 1 over 2 times pi times 50, and the value XL is going to be times 2.95. So C is going to be 1 over, it's a big figure, 926.769832. And so, if we divide that out, what we will find is that C is going to equal 0.000790416 farads. But that's kind of a crazy number, so we can say 1, 2, 3, 4, 5, 6. So we can say that is going to be, C is going to equal 2, 3, 4, 5, 6, 1079. Just make sure we got this right. 1, 2, 3, 4, 5, 6. Yeah, 0.01 farads. And that's going to be the value of capacitor. You won't get that off the shelf, but you get something pretty close to it. And then that will bring these two back into phase with each other, so you don't have those kind of losses. Hope that's been helpful to you. Thank you for joining me on my little talk, and I'll see you again next time. Thank you very much.